Welcome back to this course on Fundamentals of Computer Architecture. In this lesson I will show how the code presented in the previous lesson can be scheduled to reduce the number of stalls. Now we have everything in place to show how this loop will be executed. Here I show again the loop that will be executed on the pipeline processors and the table of pipeline latencies. With these latencies the loop will be executed like this, with 4 stall cycles. First, a stall is required between the load double and the add double, because the result of the load is not available until the end of the mem stage of the load, as indicated by the red arrow. Then 2 stall cycles will occur between the add double and the store double, because the store consumes the value of the load double, as the green arrow shows. And finally, another stall cycle occurs between the add immediate and the branch not equal, since, as explained before in the table, we assume that branches take place in the instruction decode stage. So every iteration requires 10 clock cycles, 5 instructions, 4 stall cycles, and the no operation in the branch delay slot. In other words, the efficiency is only 50%. Let's see what we or the compiler can do about it. Here's again how the loop is executed. We want to schedule, reorder the instructions in the loop in order to eliminate some or hopefully all of the stall cycles. The first question is, can we move a later independent instruction between the load and the add double to eliminate the first stall cycle, shown here in red? Do you see which instruction can be moved there? The add immediate can be moved up and scheduled between the load and the add double, as shown here. However, not the add immediate. Now the add immediate instruction is executed before the store double, which uses the result R1 of the add immediate. Therefore, we need to change the offset of the store double from 0 to -8, so that the correct memory address will be used, as indicated by this red arrow. Now only 2 stall cycles remain. Can we improve this code further? I give you a hint. Can we move an instruction in the branch delay slot? I give you another hint. Yes. The store double can be moved in the branch delay slot, since the branch does not depend on it. This also eliminates another stall cycles, because 2 cycles remain between the add double and the store. Can we improve this further if we restrict ourselves to scheduling single loop iteration? Unfortunately, the answer is no. The critical path of an iteration is given by the load double, the add double and the store double. These 3 instructions all depend on each other and require at least 6 cycles to execute, given the pipeline latencies. So we end up with 6 clock cycles per iteration, but only 3 instructions are really useful and necessary: the load, the add double and the store. The other 2 instructions, the add immediate and the branch, are overhead, are loop overhead. Next, I will use loop unrolling to first reduce the loop overhead, and second, to create more possibilities for instruction scheduling. This completes this lesson. Thanks for watching. In the next lesson, I will show how loop unrolling can be applied to further improve the performance of our code. Stay tuned.